Welcome to this explainer. Today, we're going to uncover the incredibly violent tectonic history hidden right beneath some of the most beautiful islands on Earth. You know, if you've ever looked at a picture of a pristine tropical island and wondered, how exactly did that get there? Well, you're in for a really fascinating journey. Let's get right into it.
So what violent secrets actually lie beneath the tranquil coral atolls of the Indian Ocean? Let's dive into this wild paradox. On the surface, we see these peaceful coral paradises, right? But underneath, they're sitting atop a structurally violent and deeply contested underwater mountain range. We're going to look at exactly how a piece of an ancient continent was stretched, broken, and essentially deep-fried by the Earth's mantle, literally creating the very foundations of these islands.
Section 1. A hidden underwater mountain range.
To start off our geological detective story, we need to know exactly where to look. Here we have the Laccadive Ridge. It's a massive submarine structure forming the northern part of the 2,500-kilometer-long Chagos-Laccadive Ridge system, sitting right off the west coast of India. It averages about 270 kilometers in width, and as you can see, it runs perfectly parallel to the mainland, acting like this massive, hidden boundary right under the sea.
And this brings us to our very first clue. Despite its absolutely massive size, the Laccadive Ridge is what geologists call an aseismic ridge. What does that mean? Well, essentially, it's a submarine mountain chain that is tectonically quiet. It doesn't experience active earthquakes. So, unlike the mid-ocean ridges where tectonic plates are actively tearing apart and shaking things up, this ridge is just kind of sitting there. But don't let that quiet exterior fool you for a second. The origins of this thing are anything but calm.
Section 2. The Great Geological Identity Crisis. You see, this quiet exterior hides a decades-long scientific debate about how this colossal structure actually formed. For years, scientists were completely split into two camps. On one side, you have the oceanic hotspot track theory. This camp argued that as the Indian tectonic plate rapidly moved north, it basically dragged over the Réunion Hotspot, which is this massive blowtorch of magma from the Earth's mantle, leaving behind a trail of oceanic volcanoes. On the flip side, you had the continental sliver theory. These folks argued no, this wasn't oceanic crust at all, but rather a sunken, stretched fragment of the ancient Darwar Craton, basically a giant piece of mainland India that just broke off.
So which is it? Well, the crucial point here is that recent high-tech geological surveys have finally given us an answer, and they lean heavily toward a pretty fascinating reality. This is no standard ocean floor. It really is a thinned continental sliver derived from the Darwar Craton. But, as you can imagine, actually proving that a chunk of continent is hiding beneath miles of ocean and volcanic rock, yeah, that isn't exactly easy.
Section 3. Decoding deep seismic clues. To prove this continental theory, scientists had to look deep underground. Now, obviously, we can't easily drill 20 kilometers down into the Earth, right? So instead, they used seismic waves to create a sort of forensic X-ray of the Earth's crust. Just take a look at the distinct layering mapped out by these seismic velocities. Since seismic waves travel at different speeds depending on the density of the rock, it gives us a clear picture. At the very top layer, from 0 to 3 kilometers, we have light sediments. Below that, a volcanic cap. But look at the depth between 6 and 11 kilometers. The seismic velocity there drops right into the 5.8 to 6.4 kilometers per second range. And guess what? That is the exact signature of ancient Precambrian continental crust. It's a dead giveaway. However, things get weird because it's sitting directly on top of something unusually fast and incredibly dense.
That super dense bottom layer from 11 to 25 kilometers deep, that's the result of a process called magmatic underplating. Try to imagine intense heat and heavy, high-density magma from a mantle plume deep within the Earth rising up. But instead of breaking all the way through to the surface to erupt, it just pools and solidifies right at the base of the crust. It literally blasts the bottom of the continental sliver with heavy, mafic igneous rock. Because of this massive, sustained injection of magma from below, this underplating resulted in an unbelievably thick crust. The distance down to the moho, which is the boundary between the crust and the mantle, is between 18 to 25 kilometers deep here. To put that into perspective, your standard run-of-the-mill oceanic crust is only about 6 to 7 kilometers thick. So what we're looking at is a huge, bulky root supporting this entire ridge.
But here is the really crazy part. Conversely, if we look at the effective elastic thickness, which is basically just a measurement of the lithosphere's mechanical strength and rigidity, it's a mere 3 to 4 kilometers. Normally, an ancient continent is cold and rigid with a very high elastic thickness. Finding such an incredibly low number proves that the continental crust of the Laccadive Ridge was severely weakened, thinned, and stretched out like warm taffy long before that hotspot magma ever even hit it.
Section 4. Tearing apart an ancient supercontinent.
Okay, let's move to the timeline and see exactly how this specific sequence of destruction built the ridge we see today. Tectonically speaking, this was a multi-stage disaster. First up, about 88 million years ago, the massive supercontinent of Gondwana tore apart, separating India from Madagascar. This violently stretched the crust. Then, between 78 and 76 million years ago, this stretching caused the crust to melt and trigger highly acidic pre-plume volcanism. And finally, the knockout punch. Between 65 and 60 million years ago, this already stretched, weakened sliver suffered a massive, direct strike from the migrating Réunion Hotspot.
Now, if you want absolute proof that the rifting happened before the hotspot arrived, well, this right here is the smoking gun. Scientists drilled deep into the Padua Bank on the northern part of the ridge and pulled up samples of a volcanic rock called rhyolite. Using argon-argon isotope dating, which is an incredibly precise method, they found these rocks are about 76 to 78 million years old. This unequivocally proves that the ridge experienced violent volcanic rifting millions of years before the hotspot even showed up, which, as we know, arrived much later, around 65 million years ago.
Section 5. The Réunion Hotspot Inferno. So what actually happened when that already thinned out, weakened sliver of continent finally collided with the Réunion Hotspot? Well, it created a total geological identity crisis. You can think of it as a Frankenstein crust. Step 1. Extreme lithospheric stretching isolates a narrow ribbon of the ancient Mauritia microcontinent. Step 2. Because it was stretched so thin, it had basically zero structural integrity when it finally passed over the Réunion plume. Step 3. The intense heat from the plume easily penetrated that weak lithosphere, causing all that massive magmatic underplating we talked about, fundamentally altering the crust. And finally, Step 4. The ridge essentially welds itself firmly to the side of the Indian plate.
The resulting ridge is an absolute chimera. It's a patchwork made of ancient Precambrian Darwar Craton continental crust, topped with those 76-million-year-old pre-plume rhyolites. Then it's fortified from below by massive lower crust magmatic underplating, coated on top with subaerial basaltic flood traps from the hotspot. And eventually, because it was just so heavy and the heat source moved away, it began subsiding, basically just sinking right down into the ocean.
Section 6. From Fire to Coral Paradise.
But this fiery, chaotic trial eventually had to end. As the Indian plate continued its rapid journey northward, the volcanic activity of the hotspot migrated south, eventually forming the Maldives and the Chagos archipelagos on much more standard oceanic crust. Up north, the Laccadive Ridge finally started to cool off, and as it cooled, it became denser and subsided beneath the sea. This subsidence was a real game-changer because it allowed marine life to take over, eventually building the stunning, vibrant coral atolls of the Laccadive Islands we know today, right on top of those sunken volcanic peaks.
Understanding this incredibly complex tectonic history completely changes how we view these seemingly simple coral islands. And honestly, it leaves us with a pretty massive question. If a literal piece of an ancient supercontinent was hiding in plain sight right under the Indian Ocean, what other hidden microcontinents are resting beneath our oceans right now? Just disguised as simple islands, waiting for their seismic secrets to be decoded? Thank you so much for joining me on this explainer, and remember to always keep questioning what lies beneath the surface.